Hey everyone, welcome back. This will be part B of lecture 2, where we're discussing area. In the previous example, we walked through estimating the area between, in the interval 0 to 2 for f of x equals negative x squared plus 5. And in that example, we started with the curve and we broke it into 1, 2, 3, 4, 5 regions. And we used the rectangle method of exhaustion, but we only used n equals 5 regions, 5 rectangles / rectangles, right? But we calculated the area using the right-hand side and the left-hand side, and we came up with some estimates for the area. We estimated the area to be between 6.48 and 8.08. That's what we came up with for our estimate for this function. Now, it's not important what we got as an answer. What's important was the methodology that we deployed there. And what we'd like to do now is kind of take that methodology and generalize it a bit. So we want to attempt to generalize this example. Okay, sometimes it's easy to do that, sometimes it's very hard to do that. In this case, it'll be easy because we worked it out ahead of time. But so what we want to, let's just kind of have a picture at the ready, right? So we've got some function f, we've got some interval from a up to b that we're interested in, and we want to estimate the area under the curve using this method of exhaustion. Okay, so we're going to want to start each time by subdividing the interval. So begin by subdividing the interval into some number of subintervals, and we'll say into n subintervals. Okay. Now, it's important that the subintervals have the same width, right? And so we're going to begin by subdividing the interval into n subintervals, each of width. And we're going to introduce notation here that will be used later. Delta x, the change in x, the difference in x, is going to be used to denote the width of the subintervals, and we're going to say b minus a over n naturally, right? So you take the width of the whole thing, divide it into n parts, and that's the width of each part. Okay, so you can think of it like this. So you've got on one side, you've got a, and now technically you're going to have a plus 0 times delta x. So whatever that width is times 0. Okay, that's going to be less than a plus 1 times delta x, okay, which is going to be less than a plus 2 times delta x, right? So on and so forth. Okay, so then that'll be less than a plus n times delta x. Okay, so this is just telling you the endpoints of the intervals. That's this string up here. So here's the endpoint of the first interval. Here's the endpoint between the first and second interval. Here's the endpoint between the second and third interval. And here's the far endpoint. Okay, this would be basically equal to b, right? Yeah, I won't put that on there yet, but that's the idea. So this would be basically cutting this into all of the different pieces. Okay. Now, f is a continuous function, so that's important. Okay, by assumption, we're going to assume that f is continuous. It needs to be continuous in order for this process to work. And so f being a continuous function means that there's going to be a max and a min value of f for each interval. Okay. Okay, so if f is continuous, then there will be a max and min value for f in each of the n intervals. And this is by just the extreme value theorem. Okay, very good. So we're gonna use the following to denote those pieces. So f of little mi, okay, that's going to be the min value of f in the ith subinterval. Okay, and then f of big Mi will be the max value of f in the ith subinterval. Okay, so you got a minimum and a maximum. Now, nothing cryptic here. I know that this, maybe seems a little confusing, but let's just draw the picture here. It's always nice to have a nice picture. Okay, so you've got your curve coming through here, and let's just indicate an interval here. We'll say A is way over here and B is way over here. And you're going to have some interval here of width. This is obviously not drawn to scale in any way, shape, or form. But then on this interval, you're going to have a minimum value of f, right? And that would be this end point as drawn. Okay, and then you're going to have some max value of f, which would really be the other side, right, in this case. Okay. And then depending on how you set this up, whether you want to use the inside or outside, different things will come into play here. So this is the setup, right? So you've got the minimum value over here, you get the maximum value over here, delta x is the width. And so what we're going to define now are what are called the lower sums and the upper sums. Okay. So the lower sum, okay, in this case is going to be, we're going to use a small n. Okay, the lower sum, little s of n, that looks like a big S, doesn't it? Sort of depends on how little you want it to be, but okay. So the lower sum here is going to be I equals 1 up to n of, obviously, the smaller side of things, the minimum in each interval, times delta x. Okay, and then contrast that with what's called the upper sum, which we'll use a big N or big S for. So big S of n, and I guess it's all in how you relate the S and the N in terms of which one looks bigger than the other. So that's going to be I equals 1 to n of f of big Mi. Right, so hopefully it's clear, right, like why this would be the lower sum and why this would be the upper sum. Like the lower sum is going to be based on the rectangles that are underneath the curve, and the upper sum is going to be based on the rectangles that are above the curve, right? So every region is going to have, an upper sum and a lower sum based on the minimum and the maximum. Okay, so something to note, it's probably obvious, but in case it isn't, the area of the inscribed rectangle will be equal to f of little mi times delta x. Okay, and that's going to be less than or equal to area generated by big M of I, f of big M of I times delta x, which would be the area of the circumscribed rectangle. Okay. Okay, so you're going to have the two rectangles, right? We just kind of drew that. You can, so obviously the area of the inscribed rectangle would be calculated using this, and that's clearly going to be less than or equal to the area calculated by f of big MI, right? By the circumscribed rectangle. Okay, right, and so clearly from this it would follow that little s of n will be less than the true area, less than or equal to the true area, which would be less than or equal to big S of n. Okay, so lower sum will be less than or equal to the true area, and the upper sum will be greater than or equal to the true area. Okay. Okay, all right. So, we're kind of working towards having the notation necessary to kind of generalize this process. Right, so now we've got this lower sum, upper sum idea. We've got this relationship between the lower and upper sums. We've got some convenient notation for denoting those two pieces. Okay. Let's do an example with the stuff we've set up so far. We want to find, so given f of x equals x squared on the interval 0 to 2. Okay. Let's find the upper and lower sums. Okay. All right, so let's just draw a picture just so we know what we're dealing with. Y-axis, x-axis, 1, 2, right? So we know that 1, 2, 3, 4. This guy is up here, there, and then here it should be right there, and then there it's there. So it kind of looks like this. Oh, it's terrible. It kind of goes like that. Okay, and this is f of x equals x squared. Okay. All right, and so what we're interested in is this region here. We want to find the upper and lower sums on that interval. Okay, so kind of go through the steps here, make sure we can follow this. We want to partition the interval into n subintervals. That's the starting point. We'll call it delta. Call that the subinterval with delta x, and then delta. Well, I should write width delta x, and that's going to be equal to b minus a over n, which would be 2 minus 0 over n, which is 2 over n, right? Make it very clear where this 2 over n is coming from. Now, in this example, because f is increasing from 0 up to 2, right, which side is going to be the max and which side is going to be the min? Well, since f is increasing, the min value on each interval is going to be the left endpoint. Okay, so the min value, that's going to be your MI. The max value will be the right endpoint. That's your big MI. Okay, so important to note. Now that's going to vary from function to function and region to region. Certainly if you go from 2 over to 0, it's going to be the exact reverse, right? So, but that's okay. That's okay. In this case, that's the way it works out. Okay, so the minimum value will be along the left-hand side of each interval, and the max value will be along the right-hand side of each interval. Okay, now what are those endpoints of the intervals? Okay, well, this is where we have to be a little bit careful. Okay, so we're basically trying to find mi, right, and then I is going to go from m1, m2, m3, and all the way up to m of n, right? And so what we can use here is for the left endpoint, for the left side of each interval would be 0 plus, and then we're going to say I minus 1 over the width of the times the width of the interval 2n. Okay, now notice what happens here. Okay, so for the first one, when I is equal to 1, we get 0 plus 1 minus 1 times 2 over n. So I'll just write it, 0 plus 1 minus 1 times 2 over n. And that tells us, and that's just a 0, right? M2 would be 0 plus 2 minus 1 over 2 over n. And here you're going to get a 1, and 1 times 2 over n is 2 over n, right? And then when you plug in I equals 3, 0 plus 3 minus 1 over times 2 over n, and you get a 4 over n, right, and so on. And what happens down here, you get 0 plus n minus 1 times 2 over n, and so you get twice n minus 1 over n. Okay, that's the left hand. These are the left endpoints. Okay, now the right endpoints are going to be the big mi's, and for that we're going to use 0 plus just I times 2 over n. Okay, really straightforward, right? Okay, so then m1 is equal to 0 plus 1 times 2 over n, which is 2 over n. Let's make sure we're going to follow this here. All right, so notice the right-hand endpoint of the first interval should be equal to the left-hand endpoint of the second interval, right? So you can see that that aligns. Right, this goes from 0 up to 2n. This one starts at 2n, or you know, the left-hand endpoint would be 2n. So then m2 would be 0 plus 2 over 2 of n. So that's 4 over n. m3 would be 0 plus 3 times 2 over n. 6 over n, right? And so you can see that these are going to be in alignment. And then these are big M's, sorry, make sure they look big. Otherwise you'll confuse yourself. Big M of n is 0 plus n times 2 over n, which is 2n over n, which is 2, right? So this one would be the beginning of the last interval, and then this would be the ending of the last interval, and of course that should equal 2. That's the upper bound, right? Okay. Okay, perfect. So these are the right endpoints. Okay, so we'll just basically be calculating the interval, or sorry, the rectangles based off of first this index set for the lower sum, and then the upper sum will be based off of this index set. Okay, so we'll use these, just to write this down, use these to calculate the lower and upper sums, right? So lower being using these, and then upper being using those. Okay. All right, so let's do that. Let's do that calculation quick. So start with the lower sum, little s of n. That's going to be equal to the sum from as I goes from 1 up to n of f of little mi times delta x. Okay, this would be the height and the width. Okay, that's the sum from I equals 1 up to n of f of, and now what is mi? It is 2 times I minus 1 over n times 2 over n. Okay, so again, height, width. Okay, and now we have to actually plug in the function. Remember, the function is f of x equals x squared. So we got to plug that in. So here I would have 2 times I minus 1 over n squared times 2 over n, like so. Okay. And then we can sort some of this out. I equals 1 to n. Now let's see here. Well, we're just going to have to just do the math here, aren't we? So we'll pull the 2 over n out, actually. Okay. And so then inside here, we're going to have 4 over n squared, and then it's times I minus 1 squared. Okay, 4 over n squared. That can actually come outside as well, but we'll leave it there for now. And this will be I squared minus, let's see, so I minus 1, I minus 1, I squared minus 2i, minus 2i plus 1. Okay, we've got that. And then let's actually pull the rest of this out. So 8 over n cubed, I equals 1 to n of I squared minus 2i plus 1. Okay, doing good so far. And now what are we going to do? Well, we're going to break all this apart here. So you got an I squared, an I, and a constant. Okay, so the I squared, we'll actually just do it all here, just to make sure that everybody is following. Okay, so just kind of breaking that sum apart. I realize that we just learned this notation at the beginning of the class, and so this is still probably a bit of a stretch. But hopefully you're following. You can remember we can break the sums and differences apart into different sums of sums. Okay, and then I'm going to flip to a new page here. Okay, and when I do that, we'll have, we can take this and kind of figure out what each of these is worth. So it's equal to 8 over n cubed. Now the I squared, that's going to be n plus 1, 2n plus 1, all over 6. Okay. And then it's going to be minus 2 times. Now what is the sum from I equals 1 to n of I? Well, it's going to be n plus 1 over 2. And then plus, well, this is the sum of 1 up to n, so it's 1 times n, so it's just n. Okay, so we've got this. And we can, let's see, we can sort all of this out. And basically we would have to get like a common denominator of 6 here. Okay, so we can do that. I think I'm just going to kind of, well, no, we'll push through it. So we'll multiply this. This guy's good. We'll multiply this by 3 and that by 6. So you've got n plus 1, 2n plus 1, minus, now this would be 2 times 3 is 6, n plus 1, plus 6n all over 6. This is a very, realize this is a long, arduous calculation, but it's useful to go through it and to make sure that everybody is following along here. And we'll pull the 6 out. And let's expand this straight away. So let's see, we'll get n squared plus n times 2n plus 1 minus 6n squared minus 6n plus 6n. Right, so just kind of distributing there. And here you're going to get 2n cubed plus n squared plus 2n squared plus n minus 6n squared minus 6n plus 6n. Okay, so you get that. And then a bunch of this stuff is going to collapse down, right? So like clearly these will go away. And ultimately what you end up with here is 8 over 6n cubed, and you get 2n cubed. Okay, and then minus 3n squared. So here you're going to have 2, 3, and then minus 6. So minus 3n squared. And then just plus n. Okay, and so, you know, you can sort of simplify this down a bit, and you end up with, what is it? Looks like 8/3. That's the first term. Minus 4 over n Yes, 4 over n plus 4 over 3n squared. Okay, so that is the lower sum. Okay, that's the lower sum. All right. Now we have to do the same thing for the upper sum. Okay, so the upper sum. Now it's very similar. Like the calculation is largely the same. It's just, you know, some of the expressions will change and the terms look different. But big S of n is going to be equal to the sum from I equals 1 to n of f of big Mi times delta x. Okay, which is similar to what we saw before. It's actually easier. I equals 1 to n of f of 2I over n times delta x, which is 2n, or sorry, 2 over n. Okay, and then substituting in the actual function, which is x squared, remember, you get 2I over n quantity or you know, the squared times 2 over n, like so. And this one you get 2 times 2 is 4 times 2. You can pull out an 8n squared. Let me see here. No, 8n cubed times the sum of I equals 1 up to n. Now what's left in here? It's going to be the I squared, right? So you'll have an I squared there. This one's actually quite a bit easier to work with. And so you get 8 over n cubed. And now what is the sum of I equals 1 to n of I squared? Well, it's n times n plus 1 times 2n plus 1 all over 6, just like before. And we can simplify this similar to before. So 8 over n cubed, and then we get, let's see, I can kind of look up above and see what this amounted to. So you should get 2n cubed plus n squared plus 2n squared plus n all over 6, like so. And then obviously you can combine some terms here, and you get 2n cubed plus 3n squared plus n all over 6. Okay, so I know we're getting very close to the end here. Very good, very good. That all compact, you know, can be broken apart. We want to kind of break the terms out so we can see what they all are. It can be written as 3 over 4n cubed times 2n cubed plus 3n squared plus n, which is, now here you're going to get 8 over 3 plus 4 over n plus 4 over 3n squared. Okay. All right, so that is what you get at the end here. Okay. All right, so now this is going to be our upper sum. Okay. All right, now notice, of course, that our previous inequality should still hold, right? So our lower sum, S of n, we found was 8/3 minus 4 over n plus 4 over 3n squared. And this is obviously going to be less than what we just calculated for this upper sum, which is 8/3 plus 4 over n plus 4 over 3n squared, which is big S of n. Okay, so that's good. That's good. Now, the really nice thing here is that, I mean, so you can kind of see that it's really just this 8/3 value minus something, and then for the lower sum, and then plus something for the upper sum. Okay, so some of you may be thinking, hey, what happens if you take the limit of these expressions as as n goes from up to infinity, which would be equivalent to saying let's increase the number of rectangles being used in the estimation, right? So right now it's just set, we just say n could be 5, n could be 10, n could be 1,000. What happens to this expression and the relationship between the two expressions specifically as n increases without bound? So we can do that. Limit as n goes to infinity of little s of n is the limit as n goes to infinity of 8/3 minus 4 over n plus 4 over 3n squared. Now what happens here? Well, this is 4 divided by n. N is growing without bounds, so this term here is going to go to 0. This term is also going to go to 0 for the same reason, and so we get a limit value of 8/3. Right? So the lower sum will converge to the value 8/3 as n grows without bound. Does the same thing happen with the upper sum? It'd be nice if it did. Let's see. Of course it's going to. Right? We can see that. 8/3 plus 4 over n plus 4 over 3n squared. Right? So obviously for the same reasons, this is going to 0, that's going to 0, and we get 8/3. And lo and behold, the upper and lower sums have the same limit, which means that it doesn't matter. It doesn't matter if you use the lower sum or the upper sum. As n gets larger and larger, the two values converge to one another. They are equal. And so that gives us a beautiful theorem that we can use here. Let f be continuous. And we'll say non-negative on the interval AB. Okay. Then the limit as n goes to infinity of the lower sum is equal to the limit as n goes to infinity of the upper sum. Okay, so because the lower and upper sums are the same as n goes to infinity, to find the area, we're free to choose either endpoint, or, as it turns out, an arbitrary value within each interval will work just as well. Okay? So basically, we can choose the upper or lower sum, and we get the same answer in the limit. Okay, that's great. That's great news. That's the kind of thing you want to see. Okay, so so that is a good example of how to kind of generalize this process. Okay, so let's go ahead and use this to create a definition for the area. I'm going to actually switch pages here. Okay, so here's a definition, which will be intuitive now since we've gone through this, but it would have been complete mayhem had we not gone through this example. Okay, so definition. And this will be the area of a region in a plane. Okay, so we'll let f be a continuous and non-negative function on the interval AB. Okay, so f is a continuous and non-negative function on the interval AB. The area bounded the area of the region bounded by the graph of f, of course, the x-axis, and the vertical lines x equals a and x equals b is, okay, here we go. So it is area equals the limit as n goes to infinity of the sum of from I equals 1 up to n of f of ci times delta x. Okay, now notice here xi minus 1 is less than or equal to ci, which is less than or equal to xi. Okay, it just means that ci is in the ith interval, and where delta x is equal to b minus a over n. All right, so that's just very concise wording for basically the derivations that we just did. Okay, the width of the subinterval, of course, right? So the width of the ith subinterval is delta x, right? So it's, I mean, it's, you can calculate it as b over a minus n, but it's technically speaking going to be just, should be equal to xi minus 1, right? So the two adjacent endpoints. Okay, and so just a picture quick. Let's make sure to drive this home. Okay, so you got some function, you've got a and b. Okay, right, so this is your x equals a line, that's your x equal b line, that's the x-axis, and that's the function f. Okay, f of, well, let's create an interval here of interest. This is obviously a very wide interval. This will be I minus 1, that's xi, and then somewhere in there is a ci. Okay, and the width here would be b minus a over n, and ci, of course, is just, you know, this that height right there, right? Okay. Okay, very good. All right, so that's basically the same derivation as what we just did, right? This is just, you know, kind of like even more general language and sort of summing it all up. Okay, sort of a let's sum it all up kind of thing. Okay, let's do a couple more examples really quickly. This is kind of taking a little while, but let's find the area under f of x equals x cubed. So that that function, and then on the interval from 0 to 1. Again, not getting too exotic with the functions or the intervals yet. So we're going to need, you can choose left endpoints, right endpoints. I mean, it's almost always better, I think, to choose the right endpoints, just a little more convenient. So we'll choose ci to be equal to, starting with 0, so it'll be 0 plus whatever the width of the thing will be, which will be I over n. Right, so the width of the thing will be 1 over n, right? So I guess I should write that. Delta x is 1 over n. Right, so okay, I just want to make sure this is clear. I shouldn't skip steps. So ci equals 0 plus I times 1 over n. Right, so you figure out the interval width is 1 over n, right, because it goes from 0 up to 1. So the interval width for n intervals will each be 1 over n. Total length is 1 over n. So then the right endpoint is just going to be I times 1 over n, right? So 1 times 1 over n, 2 times 1 over n, 3 times 1 over n times 1 over n, right? So it'll just break that up like that. Perfect. Okay. And I think it's better to write it as I over n, obviously. Okay, so then the area will be equal to the limit as n goes to infinity of the sum of I equals 1 up to n of f of ci, that's your height, times delta x. That's your width, which is equal to the limit as n goes to infinity of, let's see, so this is x cubed, so it'll be I over n, this guy here, cubed times 1 over n. Okay. And so we can pretty quickly figure this out. So you can pull 1 over n to the 4th outside of the sum. So you still have limit as n goes to infinity of 1 over n to the 4th times the sum from I equals 1 to n of I cubed. Okay. So the limit as n goes to infinity of 1 over n to the 4th. And now what is I cubed? Well, it's not too bad. That's n squared and then n plus 1 quantity squared over 4. So it looks like that. And we can crank this out really quick. The limit as n goes to infinity of 1 over n to the 4th times, well, you know what? I'm going to do it slightly differently. Equals limit as n goes to infinity of, let's expand this up top here, n squared plus 2n plus 1 all over 4n to the 4th. Right, so that's the sum, right? We dealt with the sum here. Becomes this thing. Okay, and so the limit as n goes to infinity of this, we can expand this further, and we get n to the 4th plus 2n cubed plus n squared all over 4n to the 4th, which is equal to the limit as n goes to infinity of 1/4 plus 2 over 4n plus 1 over 4n squared. And then, of course, we can see what happens here, right? That goes to 0, that goes to 0, and we get 1/4. Okay. Perfect. All right, so the whole limit, this area is equal to 1/4 precisely. Now, remember, this is no longer an approximation once you take the limit as n moves from, as n goes to infinity. Right? It means I think if you recall early on when we were looking at the circle, I said, how many triangles will we need to make this a precise calculation of the area of the circle? We said an infinite number, right? And then so what we've done here is we've created a sum of an infinite number of rectangles. And so we get this 1/4 is the precise area. All right. How about one more example? And then we'll call it quits on area for now. I mean, we certainly won't be done with it, though. So the next one, let's say we want to calculate the area under f of x equals 4 minus x squared on the interval, let's go 1 to 2 here. Okay, we want to find the area. Same problem as before, different function, different interval. Okay, so again, delta x is equal to the width of the entire interval, which is 2 minus 1 is 1 over n. So again, so you can think of that as b minus a over n. So 2 minus 1 over n, so 1 over n. That's your interval. What about, again, let's just use the right endpoints because I think it's easiest. So your ci, in this case, will start at 1, so it'll be 1 plus something, right, to get to the right endpoint. And what's that going to be? It's going to be I times whatever the width is. So 1 plus I times 1 over n, so 1 plus I over n. Okay, so that's our CI structure, right? And so you can test this, make sure that, as you plug, if you go to the CI, this C sub n would be 1 plus n over n, so 1 plus 1 is 2, right? So you should get the end endpoint when you're if you're using a right-hand scheme here, which we are, right-hand interval scheme. Okay, so then let's set it up. Just using the theorem, the area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of ci times delta x. Okay, plug in our values here. So f of ci, so here's our ci. F of ci would be 4 minus this squared. So it'd be 4 minus 1 plus I over n squared, and then times your delta x is 1 over n. Okay, remember, this is simple, right? This is your height, and this is your width. So don't overthink it. Don't get worried that you don't have any idea what these numbers are. It's just height times width, right? We're just doing it in a systematic and easily computational way, and obviously in a way that allows us to take an infinite limit. So let's expand this. That's an n up there. When we expand this, we would get, let's see here, it's going to be 3 minus 2i over n minus I squared over n squared, right? So summing that, and all times 1 over n. Okay, and I'm kind of working quickly now, and you could obviously feel free to pause the video to make sure that this is all clear. So I'm going to basically break this all apart now. And so this is a limit, a big limit here. You got 1 over n times the sum from I equals 1 to n of 3 minus, here we're going to have the 2n squared, sum of I equals 1 to n of I, minus 1 over n cubed, sum I equals 1 to n of I squared. Like so. Right, so again, just kind of breaking this apart. Okay. And that's going to be equal to the limit as n goes to infinity of, well, we can figure this out, right? So to be 1 over n times 3n minus 2 over n squared times, now what is this? That's n plus 1 over 2 minus 1 over n cubed, and then this would be n plus 1, 2n plus 1 over 6. And all of this simplifies nicely, and I'm going to jump to the punchline here. This is the limit as n goes to infinity of, I'm going to jump kind of to the finish line, 3 minus 1 plus 1 over n minus 1/3 plus 1 over 2n plus 1 over 6n squared. I realize I'm kind of ripping through this here, but we can, this is enough to take the limit, right? We can see each of the terms separately. And so what happens here? This goes to 0, 0, 0. So I end up with 3 minus 1 plus, oh sorry, minus 1/3. Okay, and so when I do all of that, that should be equal to 5/3. Okay, so there you have it. All right, so there we have it. That's kind of relatively quick, although it didn't seem like it was quick. This is an overview of area. Now what we're going to do next is we're going to take this idea and we're going to explore it further, and we're in fact going to make it a whole lot easier to work with, right? We're going to make this process much, much easier. Okay, now it's similar to the way we made differentiation much, much easier, right? We started with, having to use the definition of the derivative, and oh my goodness, it involved a limit and the difference quotient and blah, 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 and it was, like such a hassle. This is also an enormously convoluted process. Although, it works and it's very clear and concise when you're doing it, it is obviously computationally involved and challenging. And so what we're going to do next is take this idea, simplify it greatly, and then wrap this into the idea of the integral, the definite integral, which we will define in our next lecture. All right, see you then.